How's it going, ladies and gentlemen? Mr. Johnny here again, looking at 17.1, the common ion effect. All right, so we got a problem here. It says a solution of NaF is added dropwise to a solution that is 0.0244 molar in Ba plus 2 ion. What concentration of F minus ion is needed in order for BaF2 to precipitate? Changes in volume are negligible, and they give you the KSP for BaF2 right here. So first off, let's talk about what's happening. If we had BaF2 and we're adding it to water, it would dissociate to give us Ba plus 2 and 2F minuses, right? So this starts off as a solid and it ends up as aqueous ions. So if we were to write the equilibrium constant expression for this, it would end up being just the concentration of Ba plus 2 times by concentration of the fluoride ion squared, because the solid's going to drop out. So this is going to happen whenever we're talking about dissolving a salt. So this is a special equilibrium constant that we call KSP because it is a solubility product. So that's what that number is. And they're telling us that we already know what our Ba plus 2 ion concentration is. So we know this. They give us KSP, and they're asking us what would the concentration of F minus have to be in order for a precipitate to form. So we want to get F minus by itself. So that's kind of a simple one-step algebra. KSP divided by the concentration of Ba plus 2, and that's going to give us the concentration of the fluoride ion squared. So we got to get rid of this square, and that's not the hardest thing to do. You just take the square root of both sides. So now we end up with the square root of all this equals just the fluoride ion. So now it's just a plug and chug, right? So we do the square root of 1.7 times 10 to the minus 6 all over 0.0244, and we're going to get our answer of being 0.0083 molar for the fluoride ion concentration. Not so bad. Next problem, what is the pH of a solution that is 0.5 molar in sodium formate and 0.105 molar in formic acid? Ka is given right there. So they give us our Ka, and they give us our concentrations of both sodium formate, which is going to give us our common ion right there, the HCO2, and our formic acid. So let's talk about the acid, right? We would start with HCO2H, and it's going to dissociate to give us H plus and the CO2H minus. So our Ka expression is going to be the concentration of H plus times the concentration of the CO2H minus all over the HCO2H concentration. Well, they gave us how much sodium formate there was, which is going to give us the common ion. So that we know right there. They tell us the concentration of our acid. So it's really we're trying to solve for the H plus so that we can get the pH from that. So let's do one step at a time. Let's get H plus by itself. So I'm going to have to get rid of this down here, move it to the other side. So I get Ka times the concentration of the HCO2H. And I'm going to have to divide by the sodium formate. So I divide by the CO2H minus. And that is going to equal my H plus concentration. So now it's just plug those numbers in. I'm going to get 1.77 times 10 to the minus 4 times the HCO2H, which is given as 0.105 molar, all over the 0.500. And that is going to equal, where did I put it, 3.717 times 10 to the negative 5. So that's my H plus concentration, but now I want pH, and I know that pH equals negative log of H plus. So now I'm just going to plug it in. Negative log of that 3.717 times 10 to the negative 5. And I'll get my pH of being 4.43 as my final answer for the pH. Not so bad. All right, number 3 says calculate the percent ionization of formic acid in a solution that is 0.422 molar in formic acid and 0.312 molar in sodium formate. All right, so this is just like the last problem, except a little different. Do they use the same numbers? No, right? They're not that nice. So we're going to have to do, again, our Ka is going to equal the H plus times the CO2, I'm sorry, yeah, CO2H minus all over the HCO2H. So we're going to have to do the same thing again and solve for the H plus. So we do a little algebra and we get H plus equals Ka times the HCO2H all over CO2H minus, and all those are concentrations except for the Ka. All right, so the HCO2H is just this, right? It's the 0.422, and the CO2H minus comes from the sodium formate, which is the 0.312. So I plug those numbers in, and I get my concentration of H plus being 0.000239. So now the question is, well, what is the percentage of ionization? Where did the H plus come from? It came from the formic acid. The formic acid was 0.422. So if I want percent, I got to do the part that actually dissociated, which was the H plus concentration over what I started with, and then times that by 100. The percent I get is a really small percent, 0.0567%. That's how you do that one. All right, 4 is more of the same but different. All right, so it wants the pH, so that tells me I'm going to have to get the H plus concentration somehow. They tell me how much nitrous acid I got, which will help with the H plus, but they also have a common ion here from the potassium nitrite. And they gave me the Ka, right, acid dissociation constant. So again, I'm going to use the Ka to solve for my H plus. So I write the expression out so I can figure out what's what. Right? And all those are concentrations. So I got to get H plus by itself. So I do a little algebra. You get Ka times the HNO2 all over the NO2 minus. That equals the H plus concentration. So now the HNO2 is just this number right here, and the NO2 minus is this number, the potassium nitrite. So I plug those in. Oh, my Ka is just here. So you plug those numbers in, which I guess I'll do. I guess I'll do it, right? 4.50 times 10 to the minus 4 times by the HNO2, which is 0.390. And that is all over the point. Oh, I'm sorry, I wrote the wrong number. Stop yelling at me. You don't gotta yell. Wait. Yeah. I'm sorry, I wrote the wrong thing. The HNO2 concentration is the 0.410. Right? Maybe I should get in the habit of circling that whole thing so I know that's what goes together. And divided by the NO2 minus, which is the 0.390. And I get beep bop, boop. Concentration of H plus to equal 0.000473. All right, so now if I want the pH, I got to do the negative log of that number. So I plug and chug negative log of 0.000473, and I get 3.33 as my pH. Final answer. All right. 5, last one for this topic. It says, what is the percent ionization of nitrous acid in a solution that is 0.322 molar in nitrous acid and 0.264 molar in potassium nitrite? So why don't I learn from my mistakes that I made on the last problem and circle the whole thing and go out there. So if I want the percent ionized, I got to figure out, well, how much ionized. I'm going to figure that out by looking at how much H plus I got, because that came from the nitrous acid. So again, I'm going to use the Ka equals the H plus times the NO2 minus all over the HNO2. All right, and molar concentrations for all of that. And again, I got to find H plus by itself, so I do some algebra. I get H plus concentration is going to equal the Ka times the HNO2 all over the NO2 minus concentration. So now it's plug and chug, right? Ka, the 4.50 times 10 to the minus 4 times the HNO2, the nitrous acid, which is this 0.322, all over the potassium nitrite, which is the 0.264. And I get 5.49 times 10 to the minus 4 for my H plus concentration. Now I want percent, so I got to figure out the percent is going to equal that number, how much of it actually dissociated and gave off H plus ions, that much, divided by how much I started with, which was the 0.322, and then times that by 100. And I get a very small percent, 0.17%. Final answer. That's how you do that. So, yeah, common ions. Basically, moral of the story is if you're trying to dissolve something in a solution that already has one of its ions, you're not going to be able to dissolve as much because there's stuff already there. All right? See you in class. Bring questions.